Hello friends, today we shall discuss equipotential surface and their usual picture and properties of equipotential surface. Then what is equipotential surface? A surface of constant potential is called equipotential surface, or if the potential at any point or every point on the surface remains the same, such a surface is called equipotential surface. The equipotential surface may be the surface of a body or the surface in space. And equipotential surface gives the usual picture of electric field direction and magnitude. Equipotential surface gives the usual picture of magnitude and direction of electric field. Consider a positive charge. It produces outward electric field, that is outward radial electric field in all directions. For positive charge. And if we draw a Gaussian surface to the positive charge, the Gaussian surface, it is a surface enclosed by a charge, and the surface is at equidistant from the charge. That means we draw a circle with charge is at center, and then this represents Gaussian surface. On the Gaussian surface, the potential at every point on the surface remains the same. Since electric field, it is radial, it is along the radius of the circle, then the distance of any point from the surface to the charge remains the same, R remains the same, and potential at any point is given by phi equal to k q upon r, where r is the distance of the point, and the distances of all points on this surface from the center remains the same, and charge is the same, and k is constant. Therefore, potential at any point on this surface remains the same. Such a surface is called equipotential surface. Is called equipotential surface. And if we consider a negative charge, then electric field lines are radial, but they are inward. Electric field lines are radial and inward. And if we draw a Gaussian surface about the charge, then this surface is called equipotential surface. In this case also, potential at any point on this surface remains the same, as potential is inversely proportional to the distance. Inversely proportional to the distance. And we can draw any number of such surfaces taking charge is at the center. Therefore, the distance from this surface to the center from all points remains the same. Therefore, this is also equipotential surface. And it is found that, suppose this is the surface A and it is surface B. Surface A is at higher potential than surface B, because the distance of the surface B is greater than the distance of the surface A, and as distance increases, potential decreases. Potential decreases. And the equipotential surface for uniform electric field. What is uniform electric field? If the electric field is same at all points of a net, such a surface is called such an electric field is called uniform electric field. And uniform electric field is represented by directed straight lines parallel to each other. These are the lines parallel to each other. The spacing between the lines remains the same and they are directed in the same direction. Such an electric field is called uniform electric field. And in an uniform electric field, if a surface is kept perpendicular to the direction of uniform electric field, then the potential at any point on this surface is the same. Therefore, the surface A is said to be equipotential surface. Similarly, here electric field changes because charge is at some position. Therefore, electric field lines are directed away from the charge. As distance increases, potential decreases. But the potential at each and every point on this surface remains the same. Remains the same. But there is a potential difference between the surface B and surface A. Surface B and surface A. And to move a charge from one point to another in an equipotential surface is equal to 0, because work done is given by W equal to Q naught into delta V or dV, where dV is the potential difference between any 2 points. Consider 2 points 1 and 2. Then what is the work done in moving a charge, test charge, from point 1 to point 2 is equal to 0, because there is no potential difference between any point of the surface. Any point of the surface. And equipotential surface for a positive charge is the concentric spherical cell. If we draw a circle with center as the positive charge, we get a spherical cell. Then potential at any point on this surface remains the same. Such a surface is called equipotential surface, and work done in moving a charge from one point to another point on this surface is equal to 0, because potential difference between any 2 points on equipotential surface is equal to 0. It is at same potential, equal potential. And if we draw a number of concentric spherical cells, the potential of the surface goes on decreases as we move away from the charge. And there is a potential difference between first and second surface. Work done in moving a charge from first surface to second surface has a some value, because there is a potential difference between two equipotential surfaces. But no work is done in moving a charge from one point to another point over equipotential surface. And equipotential surface for a dipole having a negative and positive charges. In this case, the equipotential surfaces are closer to each other. These surfaces are closer to each other in the region of strong electric field. And as we move away from the charge, the equipotential surfaces are well spaced. But in the region of, this is the region between negative charge and positive charge, where electric field is stronger. Therefore, in the region of strong electric field, the equipotential surfaces are closer to each other according to the relation E equal to minus dV upon dr. Electric field can be defined as, it is the negative potential gradient, E equal to minus dV by dr. This implies dr is equal to minus dV upon E, where dr is the spacing, the distance between the equipotential surfaces. As electric field increases, or in the region of strong electric field, the distance or spacing between the equipotential surfaces decreases. And in case of two equal positive charges, due to repulsive force between these two charges, electric field is stronger at farther ends. Therefore, equipotential surfaces are closer at farther ends or in the region of strong electric field, and they are well spaced in the region of weak electric field. And no two equipotential surfaces intersect. These two surfaces do not intersect, or surface 1 and surface 2, they do not intersect, because if they intersect, two equipotential surfaces intersect, then at the point of intersection there should be two values of potentials, and it is not possible. Therefore, no two equipotential surfaces intersect. And properties of equipotential surface. Number 1, work done is 0. Work done in moving a charge from one point to another point over an equipotential surface is 0, because there is no potential difference between any 2 points on the equipotential surface, hence work done is 0. And electric field is always perpendicular, or it is always normal to the equipotential surface. This electric field, it is normal to the surface at any point. Similarly, if you draw the electric field, it is radially outward, and if we draw a perpendicular to the equipotential surface, it also passes through the direction of electric field. Therefore, electric field is always normal to the equipotential surfaces at any point. You can draw electric field and normal. Therefore, electric field is always normal to the surface, to the equipotential surfaces. And the spacing between equipotential surfaces due to a dipole. A dipole has equal and opposite charges separated by certain distance. In this case, electric field is stronger between or in the region between negative charge and positive charge. And according to the relation E equal to minus dV by dr, here dr is inversely proportional to electric intensity, and electric intensity is stronger in between negative charge and positive charge. Therefore, spacing between the equipotential surfaces becomes closer, and in case of closer in the region of strong electric field, and spacing between different equipotential surfaces is well spaced in the region of weak electric field, and this is the region of weak electric field, and it is the region of strong electric field. And in case of two equal positive charges, the electric field is weaker in the region between the two charges, and it is stronger at farther ends. Therefore, in case of two equal positive charges, the spacing between equipotential surfaces is closer at the farther ends of the charges, and the spacing between the equipotential surfaces is well spaced. The distance between two surfaces is well spaced because there is a weak electric field in the region between two charges. Clear? And in this session we have discussed equipotential surface. For 1 mass, what is equipotential surface? An equipotential surface, it is a surface of constant potential is called equipotential surface, or it is the surface on which potential remains constant or same at every point on the surface is called equipotential surface. And equipotential surface gives the usual picture of the magnitude and direction of electric field. That is what is use of the study of equipotential surface. And the properties of equipotential surface. The work done over equipotential surface is zero because there is no potential difference between any 2 points on equipotential surface. And electric field is always normal to the equipotential surface at any point. And equipotential surfaces are closer in the region of strong electric field, and they are well spaced in the region of weak electric field. And no two equipotential surfaces intersect. It is impossible because if two equipotential surfaces of different value they intersect, then at the point of intersection potential has two values, but it is impossible. Thank you.